I'm Stephen Foskett, organizer of Tech Field Day and publisher of Gestalt IT, and we are pleased to be part of today's Intel launch. Today, Intel launched the third generation Xeon Scalable processor platform called Ice Lake internally. This is a new rev of basically Intel's mainstream server chips. These are the CPUs, the equivalent of the Pentium or the core chip that you might have in your old laptop or your desktop, except obviously much, much faster. And these chips really make up the heart, not just of the modern server platform from Intel, but the modern platform that runs just about every application. One of the things that we heard during the presentation today was that literally every cloud service provider is built on Intel Xeon Scalable CPUs, probably the first and the second generation of these CPUs. And then we saw a parade of folks coming out and saying what they're building based on Intel's third generation Xeon Scalable server platform. It's important to note that Intel actually launched the third generation Xeon Scalable platform in June last year with a special chip that was designed more for hyperscalers than for anyone else. Those are essentially now just the 4 and the 8 socket parts. It's called Cooper Lake, and that is really, you could think of it as the Facebook chip or the Google chip or whatever. Essentially this is super dense high performance for hyperscalers. Today's launch of Ice Lake essentially is something completely different. Even though they're both called third generation Xeon Scalable, today's Ice Lake launch is essentially the server CPU for everyone. I was going to say for the rest of us, but literally for everyone. Basically, every application you use uses a Xeon chip, and every next generation application is going to use one of these Xeon Scalable processors. Or maybe not. There's actually been some talk about AMD's EPYC platform. There's a lot of talk about ARM chips. There's a lot of talk about distributed and heterogeneous computing with all sorts of special purpose chips running applications. And that's really what we're going to get into in this discussion. Essentially, let's take a look at Ice Lake. Let's take a look at the next generation Xeon Scalable, and let's take a look at the real competitive environment for this chip that it's going to have to fight into. So who wants to lead us off here? What's your impression of the Ice Lake Xeon Scalable platform?
I think it's a great step forward. The 40 cores to start with, that kind of identifies with AI, where a high level of parallelization is important. I do know that Intel has been working for a long time trying to understand AI and how to optimize their CPUs and processors to accommodate and optimize those applications as much as they can. And I'm more than happy to see now that they're using DL boosts or deep learning boosts to even push this further, where it's from a hardware perspective, they're helping applications to be more efficient and go faster. So a little bit of background. Deep learning is all about doing a humongous amount of math calculations per second, right? So the ability to find a shortcut to do these calculations without losing too much precision, it's really the holy grail. If you have a solution for that, then you're golden. That's why there's so many different flavors like GPUs, FPGAs, and CPUs. And CPUs were always kind of the weakest link in the sense that they were really made not for parallelization, but more for generic applications, right? Not necessarily always high performing, but just being responsive. So I think Ice Lake there is definitely satisfying my need from an HPC and AI perspective, and I definitely like what they did.
And getting into bits and bytes talk there too, I think that it's important to see that the DL boost is probably the biggest benchmark wow from today's launch. Essentially, we've got a chip that can outperform every other server platform in terms of AI, machine learning inferencing, and even is competitive, amazingly enough, with sort of mainstream GPU cards in some of those workloads.
Right, and
really is incredible.
That's right, and I think the number one positive thing about this is that a lot of people kind of underestimate. If you go to a TPU or an FPGA or GPU, you have to recode everything. If you use the third generation of Xeon, it's x86, right? Obviously, you want to recompile with the latest and greatest compilers to take advantage of the new instruction sets. But let's not underestimate the benefit of being to reuse your existing code without recompiling and redesigning your code. There's a tremendous amount of effort that needs to go into moving your x86 code to a GPU or to a TPU. That is one of the most underrated benefits, if you ask me, to using a Xeon processor.
Yeah, I would go a step further and just say that, you know, when you think about it on the back end too, building up that infrastructure to be able to support it. So building the code is one thing, but then which infrastructure do you build to support which applications? And so now you've got a processor architecture that can take on some of these very specific workloads or more general purpose workloads. You don't necessarily have to say, okay, this stack of equipment is for this particular use case or this particular application, another stack is for something different. You're going to make some tweaks in there as you optimize for particular needs, but for folks that are really concerned about these very specific stacks, whether you're a CSP or whether you're building this internally, you know, there's a lot of concern around orphaned hardware and what that means. And so what this really gives you is the opportunity to say, you know what, I can use it for this purpose now and then use it for a different purpose tomorrow, and without having to do much in the way of switching.
And of course, that's true for different times of day, at different days of the week as well. And that's one of the things that Intel likes to talk about in terms of using Xeon for things that you might think a special purpose processor would be more appropriate for.
And I know a lot of hospital customers would be very happy to do that way. A lot of the university hospitals really struggle with those kind of things of saying, we use this hardware during the day for our normal purpose IT environment, but can we use it for calculations and all that kind of stuff during the night for the people that are on the university? So having that availability is really a big thing, if you ask me.
I think that the key word here is versatility. This processor seems to be capable of doing a lot of different things and address a lot of different use cases. And sometimes this comes with compromises and with some limitations. But in this case, the amount of features and capabilities that is stuffed into this processor seems to be capable of addressing each of these different use cases in a good enough way. I mean, for example, we mentioned before that this could put a serious competition against GPUs for AI workloads, and from what we are hearing here, this doesn't come with any compromise in terms of performance. So probably, I mean, only time will tell, but it seems that Intel did an excellent job at creating something that can adapt very, very easily to different use cases without compromises or without major compromises.
So let's take a look at some of the other aspects of the chip. Certainly the AI applications and DL Boost are really impressive. I'd also like to call attention to the fact that Intel has added a lot more cores here. I mean, we're up to 40 cores maximum. But that being said, those of you who are practitioners in the field, how many maxi-core servers are you seeing in the 1 and 2 socket range? And how many customers are going to be basically buying the middle of the range instead, where you get a little bit more bang for your buck by buying maybe a 24-core server or something?
It depends. But yeah, so with VMware doing the VTEX again, let's put it that way, and saying 32 cores per CPU is the limit. Probably a lot of them will take less cores, max 32, to keep the licensing in order. But there will be use cases where 40 cores will be very doable as well. But from a VMware perspective, it's probably going to be the 32 cores maximum size.
Yeah, that I completely agree. I mean, it's going to come back to price performance, you know, and you have to look at the pricing of it and the licensing, as Arjan had mentioned. You know, it's great to look at it in a vacuum, but in reality, as a customer, you're not looking at it in a vacuum. You're looking at it in the context of these other pieces. How efficiently, how much am I going to be able to maximize that kind of horsepower? Are there other bottlenecks in the architecture that might prevent me from being able to use all of those cores in a single system? These are all factors that will come into play. I think where it might be kind of interesting is how this plays out in the cloud service provider and how they might use these really kind of maxi core, if I could coin a term, maxi core processors, you know, in their higher end offerings. But I agree. I'm not so sure I would expect to see this in the enterprise on-prem widely used. Not yet.
Still, it is nice to see them getting beyond the limits of the previous generation in terms of core count. I think that you know, I guess we're all spoiled on cores now. You know, it seems normal to have 32 cores in a processor, doesn't it? That would have been unheard of a few years ago.
I mean, it is and it isn't, right, Stephen? Because if you're not going to use it, so great. So you've got 40 cores, then you've got 60 cores, then you've got 100 cores. If you're not going to be able to capitalize on it, and maybe there's a different bottleneck that becomes your choke point in the architecture, does it really matter? Or are you chasing the competition? And so I think it really comes back to what's reasonable. And I think we are getting past this speeds and feeds kind of conversation of who has more cores, who has greater density, to, okay, what are we going to do with this? And what's kind of reality that we're going to see in the field? And that to me is where the rubber really hits the road and where it's really going to matter.
Yeah, Tim, I think there's relevance there of what is it, Amdahl's law, I think, is the kind of the limits of parallelization, right? If you there's a piece of work that you can parallelize, there's a piece of work that you can't, and at some point, the piece of work that can't be parallelized is actually the bottleneck, right? So that's, I think, to your point of, you know, you're throwing a million cores at it, and you actually haven't sped up anything in a lot of situations.
That's right. Now, if hypothetically I could take on a single package, so using semiconductor parlance, within a single package, I might have CPU dies, I might have memory dies, I might have other dies in there, and now I can send a process to that package, actually process it, and then drop it back out of the package. Now things get interesting because now you've eliminated some of those bus bottlenecks through the process, but it does require a little bit of rethinking in your architecture too, and a little more sophistication. Again, you know, I'm talking a little hypothetical here, but those are things that I would expect to see from the different vendors kind of playing out in short order.
I do think that those 40 core servers are perfect for Kubernetes clusters where there's a variety of different types of needs. And if somebody needs a larger amount of cores, then Kubernetes can easily develop or provide those capabilities. I think that's what Kubernetes kind of brings to you. It kind of creates an abstraction layer, you know, even beyond, you know, what a typical VMware can do for you and consume all those resources. I mean, there might be some applications that require 5 cores, but if you have eight applications that all require 5 cores, it's much easier to maintain one physical box through a Kubernetes cluster than to have 8 core boxes.
You know, the other thing that I was just going to highlight that I forgot to mention is that, you know, someone said it earlier about flexibility, and there's a trade-off between flexibility and high performance. So you can get specialized performance in a very narrow band, or you can get flexibility, but you can't necessarily have both. There are trade-offs. So the question comes in, where is that balancing act to get enough performance, but still maintaining enough flexibility to make it more broadly applicable?
I've just started to look at the announced configurations of the Intel cores for this Ice Lake generation. Warning, I just started looking at the matrix, but I will say that it looks like as well that Intel is kind of reflecting on the fact that there are sort of micro segments, if you'll pardon the term, in the market in terms of having, high clock speed processors. They've got liquid cooling options, high thread processors, low power processors. They've also got industrial embedded processors with a longer lifespan. So I love the fact that they're doing that and kind of reflecting how these things are going to be used in the real world instead of just saying, woohoo, we got all the cores. And in fact, the big number, the fact that Intel now can have 40 cores, that's only a couple of parts. Most of the components are much, much less. And another thing that occurs to me here, by the way, looking at this chart, and I think it's pretty interesting, AMD basically walked away from the low core count market with their latest third generation Milan EPYC. There's no EPYC below 16 cores. Intel goes all the way down to 8. And I think that that's interesting too, because it shows that this is a platform for low to mid-range server products, not just high-end server products. This is intended to compete against the mid-range second generation EPYC, not just the latest third generation EPYC.
Yeah, you kind of stole my thunder with this, Stephen. I was about to say more or less the same, because the SKU list is impressive, it's very granular. There is plenty of models that can be easily adapted for a variety of use cases. And I think that Intel also did a very good job at grouping these different models by use case. For example, yes, as you say, there is stuff for cloud, stuff for virtualization, stuff for high performance computing, stuff for lower thermal profile and things like that. So yes, of course the 40 cores number is the flashy number that everybody sees, but they really segmented the offering in a very smart way. Maybe can we start talking about something else like the PCIe 4 introduction and the 8 channels DRAM features as well. So up to you.
Sure. Yeah, I think that actually kind of goes to some of the talk that we've had previously about using a lot of cores. We heard about Kubernetes applications and microservices and containerization. All of these things are about using lots and lots of cores. But of course, if you've got if you've got an unbalanced system, if there's one thing we systems administrators learned in terms of architecting systems, it's balance. You have to have enough of everything to support everything in the system. And so you can get a situation. I mean, obviously, if you have a system with 64 cores, but only 2 16 gig DIMMs, that system's not balanced, at least probably for most applications. So I think these are other important elements to take a look at in this Ice Lake platform. Number one, we've got PCIe Gen 4, which is, again, twice as fast as Gen 3. We also have more lanes. So instead of, 48 lanes or something, we're up to 64 lanes.
64.
Yeah. And then the second thing is memory bandwidth. So memory has gone from DDR4 up to 2933, I think, up to 3200, which is a modest boost in performance. But we now have 8 channels of memory, which is a major boost in performance. So effectively, we have 2.6 times as much PCI Express bandwidth per socket, and we also have 1.4 times as much memory bandwidth, and of course also memory expansion with 8 channels. That means that you can use more DIMMs, which means more memory. So, we're looking at like 8 terabytes of memory per socket. We're looking at, 64 lanes of PCIe 4. These are some pretty good numbers too, and help to balance that system.
Yeah, and it's interesting how you can mix and match, kind of traditional DRAM with PMEM, with obtained PMEM, up to 4 terabytes of PMEM per socket, if I'm not wrong. So that's impressive. That's really impressive.
And what you've been talking about there is on-box communication and on-box processing. You need the network in place to go between boxes too. So the other thing they announced is network cards that are capable of 200 gigabits per second They have dual 100 gig ports and active, and I'm just happy to see Intel still in that market, offering that full platform. I've been in networking for a really long time, all the way back to ArcNet. And if you wanted things to work, you would put an Intel NIC in a box, whether it was a PC or a server. And dating myself even further, when laptops started getting Ethernet connectivity, PCM-CIA cards in the laptops, we always bought Intel no matter where I was, and they just worked. Quite frankly, what's running in my customers' data centers now, I don't know what they're using for network interface cards, but knowing that Intel is still focusing on that piece of the business is relieving. It's nice to see.
Yeah, I cannot stop thinking about use cases like NVMe over TCP, and just the amount of speed that you can get from processor to processor going through the network with this combination of components.
I want to ask how the other pieces of like the Optane memory stuff ties in with the processor speeds, right? Because to Stephen's earlier point, this is kind of a holistic launch, and I know the persistent memory, right? The PMEM 200 was also announced kind of in parallel with all of this, and I wonder if that's what impact that actually has on performance and how that ties into the Xeon stuff.
Yeah, that's exactly what I was going to talk about. So when you deal with a lot of high CPU intensive and data intensive applications, the last thing you want to happen is that your server goes down for whatever reason, right? So you want to be able to what we call snapshots. And so the goal of the snapshot is to kind of safeguard all the work you have done. And traditionally, this was written to a centralized storage device, typically a SAN. And so you can imagine, all those cores then come to a complete standstill, waiting for that data to be written to a SAN until they could move forward. With PMEM, you now have the ability not only to safeguard it, but you also have it accessible through your normal memory channels, which is huge as far as I'm concerned. I mean, storage is nice, but it really, in a high performance world, storage is really a weak link, because you have to go through so many hoops in order to get the data and retrieve the data, and using technology like PMEM, or in general, I should say memory in general, persistent memory, is a huge benefit. It's fast. With DRAM, we never had enough of it, and I think PMEM is a nice way to introduce that and to solve a couple of problems we had today. It would be nice if we had so much PMEM that we didn't have to have storage in the first place, really. That would be the holy grail.
Yeah, let's think about the possibilities that bringing PMEM into these servers provides. We can do acceleration by writing, by using, for example, Optane SSDs as the backend to store data versus PMEM to store metadata. We can do caching, and we can do tiering, and we can also involve traditional 3D NAND SSDs into the picture. So we can save a lot in terms of endurance. So I mean, the possibilities are endless, and the Intel platform just bring these possibilities to the market.
On that note, I'll call out at our previous field day events, and specifically our AI field day, we had an Intel partner, Memverge, come in and talk about pretty much what Frederick was just talking about in terms of using these persistent DIMMs to create not just big memory, but big useful memory that has advanced features like snapshots and so on. And frankly, we were talking earlier about how software is a driver of hardware. Memverge is a driver of PMEM. That's for sure. I think that it's interesting too, to get to what Bruno was saying about the Ethernet 800 and what Pietro, you're bringing up with the Optane PMEM. Both of these were launched previously. They were launched before the Ice Lake platform, And it was really funny because, frankly, I think a lot of us were looking at it, and even though Ice Lake wasn't announced, even though, I mean, we suspected what they were going to be announcing, I think a lot of us were looking at it and saying, boy, there's all these little things are kind of around a big hole in the middle where there ought to be a processor with 8 channels of memory and PCIe 4 and optimization to make use of this stuff. Where's that processor, I wonder? Well, we found it. It's Ice Lake. Is that right? I mean, frankly, like look at the Ethernet 800, right? 200 gigabits without PCIe 4, it basically can't do the thing, right?
Yeah, it's kind of the ring that rules them all. It brings everything together.
Yeah, I mean, you saw the same thing with Optane too, right? There was a lot of potential with Optane, and you were kind of wondering, okay, so what is this beyond just storage and memory? And now we're starting to see how this kind of plugs in, literally and figuratively, to this architecture. And you're right, Ice Lake sits in the middle of that. The Gen 3 Xeon Scalable processor sits at the middle of that. And that's going to be a key piece. So then you add all of these technology pieces together, layer in there what we were talking about in terms of flexibility of application type, put in a little bit of software with one API, and you start to see the formation of something that is pretty unique. I don't think that it's necessarily something that folks will be capitalizing on in earnest, holistically, day one, but you start to see kind of the makings of something that could be interesting, especially when you think about that edge to cloud continuum.
Well, does anyone want to jump in here with sort of a last call analysis of the hardware platform?
I don't know if I have an analysis, but just to kind of make sure that I've gotten my notes straight, my head straight here. I mean, as far as the actual launch of Ice Lake, the big ticket news items are 8 channels of DDR memory. It's PCIe 4, right, with 64 lanes. It's a 40-core processor. Well, what am I missing on that list?
I would say that you're missing AVX 512 and some of the advanced hardware, the improvements to instruction set. And actually that goes to one of the points that was made earlier, and a point that I keep hearing again and again. Oh, it's just x86, it's just x86. They're interchangeable these days, it doesn't matter. Well, these are actually features that competitive x86 processors don't have, and previous generation x86 processors don't have. So I think that that's a big thing. Also, frankly, from my analysis so far, it looks like we've got some more cache and some tuned cache on the processors. Looks like we've got anywhere between a 15 and 20% bump in terms of performance per tick of the clock, essentially IPC. So really, I'd say that those are the big announcements here with Ice Lake. And of course, as Pietro pointed out as well, a total rejiggering of the whole product portfolio, which chips are useful in which things. And I think all of those things kind of point to what we're seeing here, which is effectively now we have a new server platform from Intel. We've got the CPU in the middle that supports all of these components on the outside. So the key components on the outside would be the PMEM200 persistent memory DIMMs. Now you can have, you got 8 channels of memory. Not only that, but the memory runs at full speed, apparently, if you're using one of those PMEM200 DIMMs, which is tremendous. So you can surround your with persistent memory. We've got PCI Express 4, which is supporting the Ethernet 800, which is just a really marvelous advanced networking interface. Like I said, 200 gigabits. Wow, that's it's a really nice card. Not that doesn't exist elsewhere, but this is a nice one. We also have the P5800x NVMe Ssd, which was launched in December. That guy is also PCIe 4. So again, you're looking at it and you're like, that kind of needs a PCIe 4 endpoint. Well, now it's got one. And of course, there's optimizations to make use of all this stuff. So I think that that's really what was announced today, was basically the whole picture, not just the chip.
Right, I agree. It's the end-to-end.
That's right. And how applications can use that end-to-end piece. So it's what's under the hood within the chip itself, what's ancillary to the chip, so touching it around the sides, but then also how the different pieces kind of sit on top of it regardless of your application, whether it's AI-based, cloud-based, etc.
And we had so much to discuss today that we barely touched the security features like SGX and crypto acceleration. That says a lot.
It does, and there was a whole other part about the 5G enablement of MIMO that we didn't dig into that I thought was interesting in the presentation as well.
So there is more here. Yeah, I mean, I think that we've got a lot to dive into. So thank you very much for this discussion. You know, kind of to follow on to Tim's kind of summary, though, I think that the truth is here, it's not a chip, it's an application that we should be excited about. And really, the most impressive things about the launch are the benchmarks of systems that are making use of all these components. You know, we heard about you know, Oracle databases and you know, inferencing and Monte Carlo simulators and so on that are making use not just of instruction sets or of PCIe lanes, but of a complete system. And I think that that's pretty exciting.